Are we getting a countdown? Okay. Good afternoon, everybody, and welcome to the fourth in our series of Geo-Congress 2024 sneak previews. My name is Brad Keeler. I'm the director of the Geo-Institute, and I am coming to you live from Pittsburgh, Pennsylvania today, the site of the Geostructures Conference, which will be this November here in this fair city. So if you want more information on that, you can, of course, get to that through our website as well, geoinstitute.org. We'll talk a little bit more about Geo-Congress in just a moment. First, we have some important details. If you don't know anything about the Geo-Institute, after you watch this today, you should, of course, head over to geoinstitute.org, and there you will find out loads of pertinent information to your geotechnical lifestyle. You'll find out that we're a technical society. We have about 12,000 members, and that we are part of the American Society of Civil Engineers. Of course, if you like what you see today, and Rod, Eric, give a thumbs up if they're going to like what they see today. You should click like, subscribe, and get notifications, and we will let you know every time we post something to the YouTube channel. This is, of course, our first live stream of 2024. This is the 7th year that we have been live streaming. So we have survived another year, entered a new one, and we are really happy to be back with all of you out in viewer land. Of course, coming up in a matter of weeks in Vancouver, British Columbia, Canada, will be Geo-Congress 2024. It is the 28th Geo-Congress and the first one to be held outside the United States. We are very excited about that. As you have noticed, we have done a series of case histories to get you ready for what you are going to experience at Geo-Congress. 2 were from the US part of the Pacific Northwest, 2 from the Canadian part, and that's what we're going to bring you today. It'll be Rod Kostaschuk from BGC Engineering, and here to host and tell you a little bit more about Geo-Congress from the University of Colorado. He is a program committee member, Eric Jensen. Eric, tell them what they're going to love about Geo-Congress.
Well, Brad, they're going to love everything because Geo-Congress is awesome year after year after year. Hello, everyone. Thank you, Brad. My name is Eric Jensen. I'm a member of the research faculty at the University of Colorado Boulder. I'm podcasting to you live here from my basement office, just outside of lovely Boulder, Colorado. As Brad also said, I'm a member of the planning committee for Geo-Congress 2024, focusing mostly on the student participation side of things. But I've been going to Geo-Congress pretty consistently for the past near decade and a half at this point, and outside of the obvious excellent technical content and great talks and other great geo nerdery. I primarily go to the Congress as a way to keep in touch with old geo friends. And I can't think of a better opportunity to add more people to your network than heading to a new country, or at least those of us in the United States. So I'm looking forward to adding more people to the family reunion in our neighbors to the north. And one of the people that I have just recently met for the first time here is Rod Kostaschuk, who is a principal engineer with BGC Engineering, based out of the lovely British Columbia, that we will all be visiting here in the next couple of weeks. He has many decades of experience in geotechnical engineering, work with foundation engineering, hydrology, slope stability, all over the power sector, oil and gas, hydroelectric, mostly within Western Canada. Currently and recently, he's been focused on slope support and stabilization using structural elements and other earthwork drainage and ground improvement measures, which leads us nicely into the talk that he's going to be giving us today, which will present some slope stabilization efforts at the 10-mile slide undertaken by the British Columbia Ministry of Transportation and Infrastructure. This project was completed in fall of 2021. It's a slide on Highway 99, just north of Vancouver, and I'm looking forward to hearing Rod tell us all about the work that they did in helping stabilize this slope. So without further ado, I hope you all do join the Geo-Congress, and I'm looking forward to Rod's talk. Thank you very much.
Great, thanks, Eric. Thanks, Brad. I'll just share it here. Okay, there we go. So, yeah, thanks again to the Geo-Institute for having me here for the nice introduction. So I'll be talking about the 10-mile slide, which is on Highway 99, design and construction of stabilization measures. Okay, so just an outline of what I'll talk about here. Some background on the slide and the site, what we did for investigation and geotechnical assessments. Then we'll go through a little bit on the concept selection phase. Why did we choose the concepts we did? Some details on the design and analyses that were done for the design of the measures. And then the fun stuff, construction, some good photos and graphics and things to look at there, and then results basically as measured by geotechnical instrumentation. And before we go on, just want to acknowledge and thank my co-contributor, Sarah Gabe from the BC Ministry of Transportation and Infrastructure, Geotechnical engineer, and also Adrian Gigax. Adrian and his company were the structural engineers for the project. Okay, so project location now. So on the left-hand side, you see most of our beautiful continent. The red dot is the project location there in the province of British Columbia, southwest corner, Canada. And in the extreme southwest corner, not shown on the map, that's where you'll be for Geo-Congress coming up. So a little bit closer view of that on the right-hand side here. You can see, I'll point to Vancouver down here on the coast, and it's about a 4-hour drive inland to the town of Lillooet, which is where close to where the slide is. On the map, you can see that from Lillooet, the most direct connection to the interior, to the city of Kamloops, which is the regional center, hospitals, all that stuff, is through Highway 99, where the slide is located. Okay. So a bit more on the background. So this picture on the right-hand side here shows first of all, it shows the tunnel earthflow outlined in the purple line, which is a 1.5 kilometer long and approximately 13 million cubic meter earth flow. And essentially what this is as the mountaintops degrade in this area and the material is weathered and altered, it falls down the slopes, forming essentially this very long soil glacier, fairly steep, moving very, very little, but it has that shape. And then down here near the bottom of it, you can see, well, right at the bottom is the Fraser River, which you'll see better in other pictures. But you can see the blue line is Highway 99, and above that, the dashed line is the CN Rail line, and you can see they both go through this red outline showing the extent of the active 10-mile slide. That slide is about 200 meters wide, about 1 million cubic meters of earth in that thing. It's located on Hocklip First Nation territory, just east of Lillooet. The basal shear zone, the bottom of the sliding mass, is around 18 meters on average at the highway. Obviously, the landslide is encompassing both the railway and the highway, so a couple of important links. And then, as a portion of the slide is affecting the railway in 2016, CN Railway supported their portion, in other words, the upper portion of the slide, through the installation of 300 millimeter diameter micropiles, battered micropiles, and a series of strand anchors installed just below the railway grade. Okay, so this is essentially on the right-hand side. This is basically the picture that was at the beginning. So here is a photo in 2015 of the highway. You can see it's a dirt road highway. And you can see also in sort of the left middle up in here, you can see some large tension cracks and movement. The excavator down here is working to remove some of the material that's pushed out over the highway. This is during one of the highway closures, and is working to both widen the road again as well as straighten it out so that traffic can resume. So in this picture, the road is closed, the highway is closed, and traffic is being diverted the long way. You can see also at the top of this photo up here on top right, you can see the timber retaining wall, and this is where the stabilization measures by CN were constructed. So the slope is above the Fraser River. It's quite a steep slope. The slide's been active since 1988. And it moves all the time, moves 5 to 25 millimeters every day, slows down during the dry periods and moves faster during precipitation events or snowmelt events. As I mentioned, there's been road closures to realign the highway a few times over the period that it's been active. That has, in recent years, that's caused single lane alternating traffic only to be allowed on the highway, and the trains have had to slow down. The most recent major retrogression events were in 2013 and 2016. And in 2016, there was an 8-day road closure. So yeah, in fact, things are so bad in Lillooet, even the highway leaving town is leaving town. That's a courtesy Johnny Harris of the CBC. Okay, so how fast has the landslide been leaving town? So this is a good illustration here on the right-hand side. In 1984, you have this very small scarp that has appeared down the slope. By the way, the yellow outline is the active slide. Fraser River down here, down slope on the right. And so, yeah, in 1984, you've got this small scarp here. It retrogressed upslope 4 years later to basically get very close to the highway, and then continued to retrogress with the slide getting progressively wider as well, moving up the slope in 93, 96, 2007, 2009, 2015. And these red lines, by the way, are largely based on LiDAR change detection assessment. So they're trying to indicate all the ground that's moving at the time of the LiDAR shots. Okay, so you can see also on this illustration here a number of geotechnical boreholes. I'll note while we're here on the highway, you can see these little orange rectangles. These are cutter soil mixing shear panels that were attempted in 2011. I'll talk more about that in a bit. And then the vectors that you see are the movement direction for the slide. So you can see obviously moving downslope. The investigations, we did geotechnical drilling, mud rotary and sonic drilling. We also did seismic cone penetration tests. The earth flow material is largely clay, and you could push cones through it in most places. We did test pits and bulk samples, and then laboratory testing, including traxial testing, consolidated underdrain traxial, and residual direct shear testing. And then monitoring, this is all prior to construction. Monitoring included slope inclinometers, and we installed shape array at the highway. We also had vibrating wire piezometers installed, and we're monitoring surface movement with prisms, survey prisms, and total station survey monitoring. The shape array was really helpful. The slope inclinometers tended to shear off relatively quickly after installation, and we were unable to determine the thickness of the shear zone, which is important when you're looking at structural support. So the shape array was able to tolerate much greater ground displacement and actually show us the thickness of that shear zone. Very helpful. Okay, so the photo on the right here is an aerial shot taking a look at the site, looking uphill. And at this time, this is when CN is busily constructing stabilization measures up there near their rail track at the top. You can see the headscarp at that time is well above the railway. So they're working in here with the drilling rigs to install, in this picture, those micropiles. So what did the investigation and assessment of the slide determine? Okay, so we have this tunnel earthflow I mentioned, this kind of soil glacier feature. It's low plastic, firm to stiff, well-graded clay, silt, sand and gravel, but it also has cobbles and boulders, in fact, up to 5 meters in diameter. But these materials, the boulders and things, they're not very durable. It's highly decomposed and altered and weathered rock in this earth flow, and so those large particles were actually quite soft. However, in contrast, below the earth flow are what we call the undifferentiated glacial sediments, and these are essentially the very coarse river deposits created by the Fraser River, which is a very large river. That material was dense to very dense, well-graded in sand and gravel, but also with significant content of cobbles and boulders, and these materials were very hard. Granodiorite type materials, so yeah, hard boulders. And but across the site, we could see that material had some quite sandy zones, but then again, some very cobbly and bouldery zones. It's kind of as you'd expect in a sort of dynamic river environment. The basal shear zone ranged in depth from about 15 to 20 meters deep at the highway, where you can see the little green car driving. And the shear zone appeared as a very black, clayey, quite fine-grained zone that had formed at the base of the earth flow material, just above those very dense sediments. Very little water pressure in the ground, some perched water tables in the tunnel earth flow in some of the coarser grained portions of that material. Okay, so now to get a better idea what this thing looks like, we're going to look at some change detection analysis using aerial LiDAR scan results for an 11-year period prior to starting any of the stabilization works. So this first picture here just shows the extent of the aerial LiDAR coverage, and it's really the entire earth flow. So you can see these kind of lineations going up the earth flow to the top, to the source zone, which is in the andesitic rocks, and all of this decomposing material. It's very steep. It just falls down the slopes here and accumulates in this gully, flowing down towards the CN Railway at the top, the highway below it, and right at the bottom, the Fraser River. So the next pictures are going to show a bit of an animation of LiDAR change detection. So what we're seeing here is a still right now, and it's showing the change in the ground in the period between 2006 and 2009. So the color coding here is blue is a negative change. Negative change means that the ground has dropped down or moved backwards from the view. And a positive change in red is where the ground has bulged outwards or moved upwards in elevation. And some of the changes that are in here are man-made. You saw the excavator removing material. So some of the changes that you see were actually caused by intervention of humans, but we'll see the movement of the slide here. So I'll start the animation. And so this is, it's not, there's some time gaps are larger than others, but you can get the picture here. The blue at the area is getting darker and deeper. The ground is bulging out. Here we are in 2011, and we're coming up on some more significant movement events here. But the material down below the highway is still bulging and falling into the river. And now we're getting into 2015 when there was some larger movements. You can see how it's bulged out at the highway and below, materials falling into the river. And there in the last couple of pictures, the headscarp of the slide jumped above the railway, and now you can see this blue ground well above the railway, and that's really the condition that you saw in that previous photo. The little question mark here is exactly that. It's a question mark. That's where we installed a couple of more inclinometers and instrumentation to monitor for retrogression of the landslide further upslope. Okay, so moving on, the picture on the right here is just a frontal view of the stabilization works at the end of construction. We'll talk a lot more about that here coming up, but you can see in the picture, again, the timber retaining wall of the highway and the headscarp well above it, and then the stabilization measures here with the hydro seeding. So concept selection, what was feasible at this site? Of course, you're trying to look for earthwork solutions. That was not good. It's quite steep, unsafe downslope. You saw the material, suddenly kind of slumping off into the Fraser River there. So in terms of constructing shear keys or toe buttress, that is very challenging. Again, uphill of the slide, it continues, the earth flow continues upslope at, fairly steep angle. Opportunities for unloading the crest are not good. And because there's not a lot of groundwater pressure, just some perched water tables, drainage measures aren't going to do a lot of good either. So the sites, you can kind of tell from the vegetation, but the site's in a semi-desert climate. It's in the rain shadow of the coast mountains. And so it is quite a dry site. And then, of course, the undifferentiated glacial sediments, they are very free draining. So they drain the entire site. So you're basically now then, with those things eliminated, you're looking at structural support solutions. And again, I mentioned before the large and hard boulders in the very dense glacial sediment below the slide mass. So if you're going to stabilize the slide, you have to tie into something stable, which the UGS is. So CSM trial was attempted there in 2011. They built those panels, barrettes, essentially across the highway, so perpendicular to the center line of the road. They were not able to penetrate very far into the underlying glacial sediments. And over the course of several months, the CSM, the bottom of these soil cement panels, sheared, slid essentially along the top of that glacial sediment, and that was it. The slide continued to move again, taking the CSM panels with it and remnants of which you can now see below the highway down there, for example, where I'm pointing. So then the feasible support measures that were deemed possibilities were drilled shaft piles, either acting as shear dowels, as a passive shear dowel type support, or as a pile wall. And then the other measure that was found to be quite effective and would be good for this project was post-tension ground anchors. So that's how we got to the concepts we did. Just a quick look at design criteria here. We wanted to improve the factor of safety, the geotechnical factor safety for the landslide by 20% approximately. And that target was based essentially on a lot of experience in the past, a lot of publications. You can improve the factor safety by that much, you really get to a state where you're not going to see much movement. And that's really was the basis for that criteria. So minimum service life of 30 years. If the slide were to continue to retrogress, the current measures wouldn't be enough. And so there's a consideration there of the design life may be based on landslide retrogression. The structure should be good for up to 75 years. Limit States design methodology was used. We followed the Canadian Highway Bridge Design Code for our design criteria for retaining walls, including the 475-year earthquake. We also designed for eventual inevitable loss of all the soil above those dense glacial sediments. downhill of the pile wall. There was no reason to believe that downhill of the pile wall things wouldn't just continue to move. So we designed for that. But one of the biggest problems, as I mentioned earlier, challenges, was that the ground is moving all the time. There's really no day where it doesn't move at least a little bit. So you have to be able to tolerate and build structures in ground that is moving slowly. So the design basis, the methodology used there is just like in a supported excavation. We work downwards from the top of the slope, progressively stabilizing it, and we also account for the movement. We account for the incremental movement that's going to occur between various stages of the construction, each row of anchor, each phase of pile wall construction. Okay, so what does it look like? There's a typical cross section here on the right, and you can see the yellowy material there. That's the tunnel Earthflow. There, the shear zone is highlighted in gray, approximately 2 meters thick. And at the bottom of the geologic cross section here are the undifferentiated glacial sediments, shown with the kind of cobbly bouldery symbol. And then up at the top of the picture, you can see CN rail line is right at the top of the section that I'm showing here. And so we start at the top, quite close to where CN built their stabilization measures, and we start building rows of anchors. From the top down, we ended up with 5 rows of anchors, each of which required a little bit of excavation to build the temporary working platform as we came down the slope. And then getting down here to existing highway grade, the lowest row of anchors essentially at the final highway grade. And then once all that's in place, we went ahead and constructed the pile wall down here. So piles first, followed by the anchors, and finally this pile cap and retaining wall that is built on top of the piles. And then finally the backfill is placed behind all of that. There's also shown in white here a temporary expanded polystyrene fill, which was a wall. You can see the shape of it there, vertical on the front side. And that was built for a temporary traffic detour. And so the traffic was up there, driving up there, still single lane. But down here on the top of the yellow material, that was the working platform for the piles on the downhill side of that EPS. Okay, so it all amounted to 276 of these anchored concrete blocks above the highway. They're each 65 millimeter diameter, design load of 2,100 kilonewtons. That's approximately, 2.1 metric tons. 200 metric tons approximately. And then we have the tied back drilled shaft tangent pile wall. That's along the highway. There's 148 piles across the 200 meter wide slide. And they're each 1.5 meter in diameter. And we have 2 out of every 3 piles are anchored with tiebacks, as you'll see. We also recognized there's always a fair amount of uncertainty building in a landslide, an active landslide. And so we had monitoring in place, we had geotechnical monitoring, which we'll talk about, in place, such that we could see how all of this was working and make changes if necessary. So to tolerate the ground movement during construction, how did we go about doing that? Okay, so upslope of the highway, those anchored blocks, those are pretty easy. The anchor heads we have grease-filled caps, and so these anchors can be readjusted. They can be tensioned higher, the tension, they can back off the load on them, whatever you need to do. We have 5 or 6 load cells on each row of anchors to see how things are going and make decisions on whether we need to adjust anything. The tangent pile wall, that was a little more interesting how we managed the ground movement with that. So in the picture on the top right here, you can see in the center of the picture, this is a composite pile. It has a permanent steel pipe shell. So it's like a pipe that's installed and then filled with concrete and a little bit of rebar. And that is sandwiched in a triplet configuration between two concrete piles. These do not have a permanent steel shell. They use temporary steel casing to construct the pile that is removed. And then, as I mentioned, 2 out of 3 piles have a tieback anchor. Those go through the concrete piles, not through the steel shell. And then a beam is constructed over the top, initially a steel whaler, and eventually a concrete beam to tie the whole thing together after the anchors are tensioned. Okay, and so how does that tolerate the ground movement? So the way it works, the composite piles are installed first, and then you do the infill concrete piles. So there's 2 concrete piles between each pair of composite piles. And so when you install the steel shell, initially it's empty. That steel shell has quite a lot of moment resistance, and it's able to resist slide movement enough such that the concrete placed inside can cure without cracking. And so once that has been done, so once that concrete inside the composite pile is installed, is cured, you install every 3rd pile, so you get this row of steel piles that now has enough strength to resist ground movement temporarily. In other words, they've improved the factor of safety sufficiently on the slide such that ground movement is arrested it's not moving anymore in the area where these piles are. That allows you to build traditional concrete piles in ground that is not moving. So you don't need to take any special considerations with regards to constructing those. And so to make sure everything went according to plan, we built into the construction specifications, there were timing restrictions for, how quickly you had to, infill the steel pile with concrete and how quickly you had to get the anchors locked off, etc. So that was built into the contract. All right, so a little bit more on the design then. This is on the right here, we have some 2D limit equilibrium stability analysis results. We did 3 cross-sections through the slide in the limit equilibrium approach. And essentially, we started out by back analyzing the landslide prior to any construction work, as well as some local cut slopes to calibrate our material parameters. And then, so once we had that sorted out, then we were able to incorporate the piles, the forces from the piles and the anchors into the limit equilibrium model. And that allowed us to do initial sizing of the piles, anchors, et cetera, et cetera. And again, the design objective was to improve the static factor of safety by approximately 20% above the existing factor of safety. And seismic loading, we also did pseudostatic to confirm that our resulting pseudostatic factor of safety was acceptable. Okay. But with a simplified limit equilibrium approach, it's really difficult to determine what will be the relative distribution of all of these ground earth loads on the structures. They're not all built at the same time. The ground is moving while you're constructing. So hence we developed a flat 2D numerical model to evaluate the construction sequence, as well as the final configuration under static and seismic loading. And so in the model, we modeled the sequence of construction. So each bench is a little excavation, and then you put in an anchor, starting at anchor 1 at the top there. And then you tension that in the model, and then you go down and you excavate in the model the next little bench and put an anchor in there and tension that, etc., coming all the way down the slope. And while that's going on, you're keeping, it's a dynamic model, and you're keeping the ground moving such that if it takes, for example, 2 months to build a row of anchors, then before you build the next row of anchors in the model, you allow the ground to move the equivalent of 2 months of ground movement. and then you build the next row of anchors. So that's the displacement control model. We had to reduce the strength a little bit of the basal shear zone here sometimes to just keep things kind of moving, like tiny little amounts, just to keep it moving in the dynamic model. And able to go down all the way to and construct the piles and in the sequence of piles as well, which we'll discuss in more detail here. And the results of this analysis mainly was to transfer the soil loads mostly for the pile wall to the structural engineer, and then the structural engineer was able to do a much more sophisticated model of the portion of the pile wall, and also incorporating these soil loads during progressive construction, but also the other loads that need to be added, for various things that structural engineers have to add on the top. Okay, and the finite element program used for the structural work was RFEM. Okay, so these are the steps in the numerical model, the FLAC model essentially, and the corresponding 3D structural model. The sequence was completed for both of them using the soil loads that came out of the FLAC model. So the initial case here, you model development, boundary conditions, and soil properties. The friction angles, the strengths had to be just a little bit different than limit equilibrium in order for the FLAC model to be at equilibrium. So that had to get figured out. And then we start with the construction sequences I described. So you install anchor row 1 and then tension it off, and you allow some subsequent slide movement, and then you move to row 2 and you do the same. And you keep going down the rows all the way to the highway. Then in the model at step 16, you install the composite steel pile shell. So only the shell, so it's the structural properties of just the steel pipe at this point. And then you slowly increase the stiffness of that to account for the hardening of the concrete inside of the pile. That's step 17. And then in the model, the additional concrete piles, so the two infilling concrete piles between each pair of composites are built in the model. And again, during this stage, the ground downhill of the piles, it continues to move in the model, but it stops moving at the pile wall and above. Okay, and then the last step is this is a tied back tangent pile wall, of course, so you need to excavate down in front of the wall, install tiebacks. So that is included in the model, including the tensioning of those tiebacks, and then finally the backfilling of the retaining wall. And the other thing is that the slide's going to continue to move, so we also had to look at what happens in the longer term, say 75 years from now. And the soil downstream has completely moved away from the wall and fallen into the Fraser River. So we had to look at that case as well. So, okay. I'm going to skip through this a little bit. This is some of the structural analysis results and the soil pressures, but essentially it shows that and when you start, as you add the anchors and as the retaining walls backfilled, the soil pressures continue to go up, and it really goes up when you remove the material downhill of the pile wall, and then it further increases if you back off the tension on some of those anchors above the hill, above the pile, up on the slope. Okay. And you can also see, of course, the big change in soil pressure as you go across the basal shear zone at approximately 13 meters depth in this particular case. This is what the 3D structural model looked like. On the left here is the actual, from the drawing, this is what the structure looks like a little bit closer up. We have model piles. Model A has the piles installed just acting as a cantilever. In Model B, there's a steel whaler is installed and the anchors. And then finally, the ultimate case, on top of the piles, we build this retaining wall, and we build the concrete cap beam and backfill behind the retaining wall. And that's the case where we also look at the effect of detensioning the uphill anchors, seismic loading, and loss of soil downhill of the wall. So there's a bit of a change in the way that the loads are applied. Again, a bit of a detail here. FLAC and the RFEM modeled the anchors in a slightly different way, but though there are equivalent models, just the 3D structural model obviously does a much better job on the bending moments, shear forces, etc. And the results of that are here. So on the left-hand side, you have your bending moment as a function of depth. And you can see the largest bending moments right here across the shear zone of the slide. And again, each of these different lines is a different point in time, the initial condition followed by, with the initial lock-off load, followed by, subsequent phases when the wall is complete, when the soil downslope sloughs away, and when you do that anchor reset. It showed us that unloading the anchors uphill of the pile wall is not the greatest idea because it puts a lot of load on the pile wall if you do that. Okay, so now this is going to be a bit of a time-lapse photography thing of construction. So right now we're looking at the landslide. We've got the pile wall, the timber pile wall in the background. And at this point in time, we're just starting on the uppermost row of anchored blocks. I'll warn you that this time lapse kind of jumps. It's not equal points in time, and there was also some gaps in construction. But here we go. You'll see the anchored blocks being constructed through the seasons, coming down to the second row there, this little winter shot. Second row is still there. You can see that we're sitting there at the same configuration for a while, which I'll explain in a bit. Now we get going again to the third row, and the fourth row, and finally the fifth row, which is down at the highway. Just going to pause there. You can see these expanded polystyrene being constructed along the lowest row of anchors. The traffic's going to be diverted on top of that. And now we're going to keep going again on the time lapse. Now the piling rigs are coming in below that expanded polystyrene, and they're putting in their piles, and they're moving across from west to east, right to left. And there was 2 piling rigs supporting cranes. You can see after the piles are installed, then they excavate out in front of those. The tieback rig comes in there and installs the tieback. So it's another winter, so we got heating and hoarding going on. And now we're getting into summer again, and we're getting to the final part of the retaining wall, the top part of it. And there we go. That's the completed configuration. That is construction. Okay. So just a few more kind of neat photos of construction. Here we are on the left, placing the precast concrete anchor block with the hole through it. And then the next step, the articulated drill on the right, is drilling through that to install the soil anchors. And on the bottom here, we are loading. Every anchor was tested and then locked off. So construction challenges, yes, we had some. So we had robotic total station monitoring going on, surveying twice daily. And so we had prisms all over the place to monitor for acceleration of slide movement, which could be, jeopardize construction work. So on the November Veterans Day long weekend, we had heavy precipitation. This was 2019. We were constructing the anchored blocks upslope, but this is what happened down at the highway level as a result of some pretty heavy rainfall. The tarp, it worked. We closed the highway for 24 hours, filled in these tension cracks, and we were able to get traffic moving again. The movement slowed down as the weather got better, of course, but it was one of these lurches. The slide does that from time to time. But looking at that, we decided to respond to that by doing a redesign. We lowered the top of the pile walls. They initially were going to be constructed near the highway grade here, but we lowered that such that we were creating a bigger excavation and kind of unloading this area with the tension cracks in order to form the working platforms for the piles and for the tiebacks. So that's why we needed this temporary EPS retaining wall, was because of the lowering of the top of the piles. But after that was all done, it was good to go. Construction was completed. There was no further delays of any kind, no further traffic interruptions. The single lane alternating traffic continued. Okay, so on the left-hand side, I've talked about most of this already, but you can see that the piling rigs have made it most of the way to the east side. The piles themselves are exposed, and the tieback rig is over here putting in some tiebacks. A couple of close-ups of the rigs, two BG40 dual rotary rigs here. Temporary, top shot shows temporary steel casing and an oscillator. And on the bottom shot, the crane is installing a stick up on the composite pile. So that's the permanent pile shell sticking up in the air there. Okay. There's the anchors being installed through the piles. The top picture on the right here, you've got your anchor is installed, and then they put in this whaler stools onto the concrete piles. And then we're tensioning them off here at the bottom. Okay, that's what it looks like just before we start pouring concrete. There's a temporary whaler, steel whaler. The anchors are tested and loaded off using that. And then all of this is encased in an integral cap beam and concrete retaining wall so once those tiebacks are tensioned, the slide is completely stabilized, and now you can carry on with the rest of the work, and ground's only moving down here on this tieback working platform. So the tarp monitoring continued throughout that construction. A little bit of rebar detailing, blockouts for the anchors prior to casting that concrete. On the top right of that photo, you can see the completed concrete work, and that's the permanent cap beam. There is the retaining wall, and on the top of that, they're just doing the rebar for the guardrail on the highway. And now a little drone video, short drone video here that will show you in the foreground. You've got the Fraser River here. It's a very large river. I believe those are chunks of ice coming down it. And there's all this black zone here. You can see how the material is just falling into the Fraser River, sloughing here. And here we are on the construction at the phase that I just showed in the still photo. And coming into the picture on the right here, you're going to see a white pickup. That white pickup, so we've got single lane alternating traffic. It is driving on top of the polystyrene fill, and you can see again the anchor on the bench below, and the completed blocks on the slope above. So yeah, near to the end of construction. At this point, the slide is essentially fully stabilized from the pile wall up. Okay. So just a little bit more. There's a photo near completion. You can see here they're removing the expanded polystyrene fill. Traffic has been diverted on the downhill side of that, right up against the top of the retaining wall that is completed here. And just some results. I mentioned that there was a bit of a delay during construction, and there was. We initially in phase one, we installed 30 anchored blocks on the top row, but then as we were preparing for the rest of the work, it was determined that the soils, those earth flow soils, actually had high naturally occurring metal content. And so you couldn't just dispose of them any old place, and they had to get a soil disposal area designed and permitted before we could carry on with the rest of the work, which involved removing the soils off site. So we ended up with a 2-year unanticipated break in construction. So this plot on the left here is the load in the anchors on the upper row, that first row. And you can see the load going up, and then we untension it. And it's going up, the design load, and then we untension it again. It's going up because the ground keeps moving. We haven't put in enough anchors to stabilize it. So it just keeps moving. This was not good. Some of these gaps here were only 2 weeks long. But then we got in phase two, which was 60 more anchored blocks in the upper 2 rows. And that was it. that was the ball game. After those anchors were tensioned, we didn't see anchor load increase anymore. It was essentially steady, a little bit of increase. We readjusted anchors from time to time. I'll show you a little bit more on the next slide, but loads continuing fairly steady. These are the loads on the lowest row of anchors with time. Interesting event, when we tightened the tiebacks in the pile wall, the load on the anchors above the highway decreased. And you can see this here. The load on the lowest row of anchors actually decreased when the tiebacks were tensioned. And then we retensioned anchors here, you can see in the summer of 2021, and then loads have continued fairly steady, most anchors. This purple line here on the east end, we have anchors located in very cracked up ground, and they continue to settle in kind of these lurches. So that's something that we continue to monitor. Slope inclinometer data showing cumulative displacement with depth. Again, you know, we got up to approximately 25, 30 millimeters in one of the inclinometers. These are located within the rows of anchors on the slope. But then by August of 2022, we're really seeing no more movement in those. We continue to monitor. And this is the LiDAR change detection work that was done using terrestrial scans after construction. And from this, you can see all this gray area is not moving. That's the zero change stuff. But down below, you know, we continue to see this movement and material slumping into the river. So again, monitoring results. Load is fairly constant over most of the anchored blocks. It's decreasing a bit at the east edge of the slide. The load on the tiebacks is beginning to slowly increase, as we expect, as ground moves away from the face of the wall. And but within the stabilized area, we've got negligible movement. And there's a couple of references for publications on the project. If you're looking for more details, the first is the geotechnical presentation, and the second is the structural aspects of the work. So right as in October of this year, or last year, I guess now, you can see that the ground is still moving downhill of the pile wall, and that continues to slough away into the Fraser River. Yeah, I'll leave you with this slide. You can look at some of our project participants here. And myself, Sarah Gabe, and a couple folks from construction. Yeah, and that's about it. That's the end. So if there's any questions, be happy to answer. And thanks again for the opportunity to present this project.
Thank you, Rod. I think my mic is working again. Okay, yeah, thank you, Rod. Fascinating stuff there. As a person who has spent a lot of time doing numerical modeling and sort of sitting in the ivory tower, it's always nice to see people, you know, doing real engineering and learning about all the flavors of what that looks like. So anyway, I have a few questions. We're going to get some questions from the audience that are popping up on my screen right now. But as we're getting those all set up, a couple questions for you from me. Was pile integrity testing completed? And if so, what method did you guys use?
Oh, yeah. Okay, good. Yes, we did do pile integrity testing. And what we used was TIP, thermal integrity profiling. And in that method, you install, you know, thermal couplers, I guess it is, a string of them down the rebar cage around the perimeter. And then you monitor temperature with data loggers as the concrete cures, and look for anomalies in that change in temperature. And we found it was quite effective. We used it in the concrete piles, and in a few cases, what we had is we couldn't take the piles cased all the way to the bottom. We were encountering boulders and things. So we had part of the pile completed open hole. And in those cases, the tip really helped us to ascertain that actually our rebar cage was a little shifted, and we made adjustments accordingly. So yeah, it was quite effective, and yeah, worked well.
Great. Another question I had. I noticed, or you had mentioned in the beginning that this is an unpaved piece of highway here. And you might have said, but I missed it. Was the highway paved immediately following completion?
Yeah. No, in all of those photos that I showed there, yeah, the highway was still just gravel. And it was intended to leave it for a period of 1 year just to make if there was any ground movement and settlement behind the wall in particular, make sure that that wouldn't impact brand new pavement. It actually ended up just getting paved this summer. There was a further delay, but it's all paved now, and yeah, looks great.
Fantastic. And then I guess following up on that is, and you had mentioned some long-term geotechnical monitoring is in place. I'm curious if you can expand on that. And also, does that stabilization system require any maintenance or anything, or are you expecting it to be sort of self-sufficient?
Yeah, right. Okay, so in terms of the monitoring, I mentioned the load cells that we have on the anchors and the tieback. So that continues. So we're continuing to monitor that. And we've actually got an automated system. So it's live. We're able to log in and see the plots of load on all the anchors at any time. So that's great. We have 4 sloping clinometers within the stabilized slide, and then a few more surrounding it that we read a couple of times a year. So that's not much labor there. And then in terms of maintenance, it really comes down, it really comes down to the anchors themselves. They require maintenance. We have, grease-filled caps on them, and it's really important to keep that maintained and to prevent corrosion in the area of the heads. So that's really what the maintenance work is about. We are proposing to go ahead this summer and retension, tighten up a few anchors on the slope that have dropped more than others in the area. And that's about it. That maintenance in the order, something like that, maybe every 5 years could be required.
Okay. A couple questions from the audience here. Clayton P asks, how did the friction angle from the lab testing compare to the back analysis results?
Not too bad, actually. It lined up pretty good, and also fairly consistent with just kind of simple residual friction angles that you get from clay plasticity. So yeah, it was a case where we actually, it lined up quite well. So it was comforting. Yeah.
That is comforting. Thomas asks, under the DCM, the constant displacement is considered in previously installed anchors. Looks like flax step 28 on the chart. How was relaxation of tension in the anchors verified in the field?
It wasn't. Yeah, once we were into construction and we were starting to see those, steady loads, from that point forward, we've only loaded, like reloaded. We haven't had to unload, and that's a good thing because the numerical modeling showed us that if we unload, that's when we can transfer more onto the pile wall. So yeah, so far we haven't needed to verify that. We don't really want to do that test because it does put more load on the pile wall.
Excellent. Bill Stevens asks, was drainage incorporated into the retaining wall design?
Yes, it was. There's drainage, of course, highway drainage, so that the drainage from there could run off. But also there were weep holes. There's weep holes through the retaining wall. And actually in one area, I mentioned we had perched water tables. Well, in one area, that manifested as a fairly steady flowing stream, like a seepage spot right near the highway. And so in that case, we built like a graded filter drain and captured that water in a drain gravel and pipe and took it through the retaining wall so it wouldn't build up over time.
Yeah, excellent. Ian Gidley, excuse me, asks, was the wall designed to retain the 10-mile slide, or would it also work for the larger tunnel slide mass? So if any of the other mass becomes active here.
Right. Short answer, nope. It's only designed for the little red outline, not the big purple outline. That's right. And so if there is a retrogression, either laterally or, upslope, it can expand sideways too, right? That would require further action. Yeah, that would require more stabilization measures. The hope is that with this, the red outline bolted down, that the retrogression won't occur, but it could still.
It is, I guess, to follow up on that, is there continued monitoring upstream of the slide to?
Exactly, yeah. So we have slope inclinometers above the headscarp at like a couple of different distances. And then also we have on the east side, the slide's a bit more active below the highway. So we have another inclinometer to monitor for lateral expansion of the slide.
Gotcha. Nick asks, what process did you follow to determine the spacing of the anchors from top to bottom of the slope? For example, why not 4 or 8 rows of anchors?
Yeah, okay. So few things on that for sure. During construction, of course, we had to have these temporary benches. And then in the long term, we wanted to leave enough of a bench that we could come back and do maintenance work on the anchors, right? And so that starts, and then how steep can you cut these slopes? We actually cut the slopes on individual benches, were cut at 1 to 1. They're very steep. So geometrically, to get from the top to the highway, you start to get constrained, and more rows actually makes it worse. Fewer rows is better, but then you get into the size of the anchors. These are almost as big as they come, so you get limited that way. So there's an optimization there for sure. It has a lot to do with being constructible and also being able to service it in the long run.
Right. Deo asks, so we've talked about uphill, but what about downhill? Have any remedial measures, or do you plan on putting in any remedial measures to control any sloughing below the slope remediation work, or are you worried about any potential impacts of the downhill stuff affecting the work you've already done?
Yeah. So we are not going to do anything to stabilize that ground. It'll continue to go and fall into the Fraser River, which it's been doing for quite a while now. So the end configuration is that all of the ground downhill of the pile wall disappears above the shear plane, essentially. And so we have assumed that in the design. So that's okay. We can lose all the soil right down to that bouldery glacial sediment. We can lose all the soil above that. The wall is designed for it. But if that's to occur, that's when the risk of lateral expansion that affects the highway, starts to go up. So, if that occurs, if movement downhill of the highway causes lateral expansion beyond our stabilization measures, then again, more work would be needed.
Mm-hmm. Clayton P. asks, were different soil strength parameters considered for seismic analysis?
No, they weren't. Because the real controlling unit is that basal shear zone with a very low friction angle, that is already at a large strain residual friction angle because the movements have been going on for years here and large movements. So in seismic, it actually couldn't weaken that material any further because it's already at residual. So that's that main controlling shear unit. But for the soils above in the model, no, they're not strain weakening either. Those clayey earth flow soils, they are not strain weakening. So we didn't include that either.
Fair enough. Nick asks, was there any concern that the additional load of the construction equipment would cause sudden catastrophic slope movement? And if so, how were these concerns addressed outside of the stuff you've already talked about?
Yeah, there was concern, absolutely, and we adjusted our pile heads to help with that problem for sure. But also the history of slide movement didn't indicate for this particular slide any such catastrophic kind of failure. It would accelerate, and as we said, could move like a half a meter in a day or even a meter in a day. So that's the kind of, but it's not like it would completely, catastrophically fail the entire thing into the Fraser River. The evidence was just based on, experience with the slide. It just doesn't do that, right? But however, certainly that was a concern, and that is why we had the robotic total station monitoring, watching for any acceleration of movement as well, both largely in the area downslope of where those tiebacks were going in. We had a lot of monitoring going on down there.
Fantastic. And as a final question, to maybe take a step back, what the decision was made to continue to place the highway there rather than moving it somewhere else? So why not realign the highway and avoid the slide altogether?
Yeah, well, you got a good look at the conditions downslope of the highway. The opposite side of the Fraser River is worse. Like it's even this whole countryside here has got a lot of geotechnical instability, right? So really the only realignment option would have been to basically go uphill above the slide and then come back down. But if you don't fix the slide, well, that's not going to work in the long term either because it's retrogressing, right? Mm-hmm. So that's why it was decided, okay, we got to deal with it here, or completely close the highway and the railway, and that was not palatable. Yeah.
Well, with that, I'm going to kick this presentation back to Brad. Thank you so much, Rod. I have really appreciate and enjoy the presentation. Thank you.
And that was a great job, Rod. And I think a testament to that is how many questions we got. Sometimes we get through these things and I feel so bad because the viewers are silent. And I'm like, oh, no, that's just the way YouTube goes. We don't have to say that today. So thanks especially to our viewers for participating today. And the people who submitted questions. That's great. You make this a much more interactive session, add a lot to the presentation, and so we really appreciate that. Eric, great job doing the moderation. This was fantastic. So again, if everybody watching liked this, and you probably did because you're here at the end, you should click like, subscribe, and get notifications. And if you do those things, we will let you know every time we post something to the YouTube channel. Be on the lookout for other big announcements about live streams, maybe from Geo-Congress in Vancouver. So if you can't join us out on the West Coast, you will be able to at least get a taste of it from your home. That will be coming up in the next few weeks. In the meantime, our next live stream is on February 6th. It is the first in a three-part series that we're doing with McAferry on rockfall mitigation. You can sign up for that at our Eventbrite page and sign up for the other two that are happening in March and April as well. So again, thanks to all our viewers. Thanks, Rod. Thanks, Eric. Great job today. Amber Davis was our producer. We will see many of you at Geo-Congress 2024 in Vancouver. You can, of course, get more information at geocongress.org. And we will see all of you very, very soon.